Welcome back to the London Futurists podcast. Could the future see the emergence and adoption of a new field of engineering called nucleonics, in which the energy of nuclear fusion is accessed at relatively low temperatures, producing abundant, clean, safe energy? This kind of idea has been discussed since 1989, when the claims of cold fusion first received media attention. It is often assumed that the field quickly reached a dead end, and that the only scientists who continue to study it are cranks. However, as we'll hear in this episode, there may be good reasons to keep an open mind about a number of anomalous but promising results. Our guest is Jonah Messinger, who is a Winton Scholar and PhD student at the Cavendish Laboratory of Physics at the University of Cambridge. Jonah is also a research affiliate at MIT, a senior energy analyst at the Breakthrough Institute, and previously he was a visiting scholar and Think Swiss scholar at ETH Zurich. His work has appeared in research journals, on The John Oliver Show, and in publications of Columbia University. He earned his Master's in Energy and Bachelor's in Physics from the University of Illinois at Urbana-Champaign, where he was named to its Senior 100 honorary. Jonah, welcome to the London Futurists podcast.
Thanks so much for having me. Super excited.
Thanks for joining us, Jonah.
Jonah, what reason can you give to our listeners for continuing to listen to this episode, rather than switching it off, complaining that they didn't expect to hear about pseudoscience from London Futurists?
My instinctual response to that is something like, certainty is usually a quite comfortable space, but I think maybe we should think about embracing uncertainty a little bit more. Certainly the zeitgeist surrounding cold fusion is that this is, as you said, a sort of one and done, case closed kind of deal. But I think that there's both theoretical and experimental motivation to spend some time working on this and really trying to understand the phenomena a little bit better. There's this rush to certainty, and I think we should embrace a little bit more of a liminal unknowing, if you will. There's a lot of work to be done, and my colleagues and I at MIT certainly think that there's a lot there that merits our time. Again, there's theoretical and experimental motivations. And then obviously, if there is a genuine novel nuclear effect here, that's interesting scientifically, and then it's also interesting technologically, and those are two different steps. But as scientists, we are keen and motivated to explore the unknown.
Skepticism is all very good. In fact, it's really the essence of the Enlightenment and the scientific revolution. But on the other hand, there are ideas which we can be reasonably confident are not true. For instance, the Earth wasn't created 4,000 years ago and dinosaurs weren't created by God to fool us. Those things could be true. We can't prove that they're not true in any more certain way than we can prove there isn't a chocolate teapot circulating around Jupiter. However, you're convinced that there's much better reasons to believe that cold fusion is possible. So what are the key reasons why you think that the majority of the scientific community is wrong?
One can hold my view and be a plenty skeptical scientist. The argument that I'm trying to make is that the embrace of the unknown is not a relinquishing of one's epistemic, skeptical, scientific mindset. Obviously, I think it's a category error to put creationism and cold fusion in the same bucket. But I take the point that there is a felt consensus in the scientific community that this is a no-go. I think it's interesting if you go back and read some of the early literature on cold fusion, which was the technical foundation for that perceived consensus. If you go back and read it carefully, it's a little bit more ambiguous than I think people maybe think of. And I've talked to some of these very established, credible scientists who were part of this theoretical argument that cold fusion is a priori impossible. And if you press a little bit, you often find that there's a little bit more ambiguity than people understand. The reasons for skepticism of cold fusion being possible make perfect sense in a certain framing. But then I think you can complicate that framing. So I would put forward that there's a lot more technical ambiguity, both on the theoretical and experimental sides, than people often perceive. And a lot of these anomaly reports in the literature have not been digested by the scientific community. But I want to be clear about this. I am not saying that there are dozens of papers that are clear and obvious and demonstrative evidence for cold fusion, or that term is a little bit outdated now. The term of low energy nuclear reactions, LENR or LENR for short, is the more commonly used terminology today. And that's the terminology that the US Department of Energy's ARPA-E, Advanced Research Projects Agency for Energy, so their innovation DARPA style program, which has a low energy nuclear reactions research program, or a LENR program, of which my MIT colleagues and I take part in. So LENR is the terminology that they had adopted. But my argument is that there are ambiguous anomalies in the LENR literature. I think it's likely that many of the LENR anomaly claims have prosaic explanations. There are experimental reports which are extremely low quality, but I think some of them don't have prosaic explanations. And I think some of them are indications of genuinely novel nuclear effects, new physical effects in metal hydrogen samples. For me, something which indicates this genuinely novel nuclear physical effect, it doesn't mean that it's a perfect, very clear, unambiguous result. I think the LENR field is in need of experimental upgrading. And I think that there is a way in which engaging with that literature without rejecting it so quickly, simply because it's not a Nature paper. This is not an A1 standard level yet. But what I'm arguing is not to forfeit one's skepticism, but to engage constructively with ambiguous, imperfect results. And that messy science, it's very often that from that sort of messy science emerges revolutionary scientific and technological results if done right. That's what my colleagues at MIT and I are trying to do.
You have commented in the past that the field of semiconductors had a similarly messy past. You pointed out a quote of one of my heroes from schoolboy time, Wolfgang Pauli, one of the pioneers of quantum mechanics, who said in 1931, "One shouldn't work on semiconductors. That is a filthy mess. Who knows if any semiconductors exist?" And thank goodness that advice was not acted on, and people continued to delve into that messiness, and eventually we have changed the entire world.
And it should be said, it was indeed a filthy mess. My colleagues at MIT and I were trying to do this sort of science on the frontier. And one of the things that I think is super important for us and very important for me is to marry one's scientific work with a very focused, actionable interest in the history, philosophy, and sociology of science, and particularly the sociology of science. One thing that I've observed is that very often people forget the prehistory of fields and what field formation really looks like. And it very often looks quite messy. So in the case of semiconductors, I think the first patent for what is now understood as a transistor, so I believe 1926 by Julian Lilienfeld. This is some 20 years before this famous physical review letter paper out of the Bell Labs solid state physics group. That's where things really got crystallized, pun intended, and the phenomena of the transistor was really demonstrably made clear and understood. And that gave rise to integrated chips and the IT revolution. But there were decades of anomaly reports, often by radio engineers, not highbrow scientific establishments. Messy, very often not reproducible. They didn't understand the importance of doping. So it might be that if you get your germanium from this mine, you get better results. It sounds quite unscientific, but actually there's a way in which a lack of theoretical grounding confuses the anomaly reports.
Let's come back to cold fusion. What are we specifically talking about with cold fusion? Can you explain low energy nuclear reactions, or LENR, as you call them? Can you explain how that works for listeners like me who don't really know their gluons from their quarks?
I think it's worth taking a step back and talking a bit about isotopes of hydrogen nuclei to start. So elements are indexed by the number of protons that they have, and then each element can have different numbers of neutrons in the nucleus, and that defines an isotope. And so you have isotopes of hydrogen, and this is the promise of fusion energy. You basically smash these hydrogen isotopes into one another, and there's some probability that they fuse, because when you have positively charged nuclei, this is like sticking two positive ends of bar magnets together. They're pushing against each other. They don't want to come together. But if you get them close enough, another force starts to dominate. Then they come together as if they were opposite ends of magnets very, very fast.
What is that other force?
The strong force is the strong nuclear interaction, which is a short-range interaction. So once you stick those positively charged nuclei close enough, once they get close enough, then they want to stick together. And it's a much stronger interaction than the electromagnetic interaction, which is pushing them apart at further distances. And the key bit about fusion is that if you have these two positively charged nuclei, if they do indeed come together and fuse, the mass of the resulting nucleus is ever so slightly less than the sum of the mass of the two reacting nuclei. And by Einstein's famous E equals mc squared equation, you can relate mass to energy, and that missing mass gets converted to pure energy. And so this is what has animated working on fusion science for many, many decades.
And what is that missing mass? So part of the nucleus disappears. Is that because the atoms go to lower isotopes, or do electrons disappear or something?
No, it's quite complicated. It has to do with the binding of nucleons. Different nucleon arrangements have different strengths of how tightly bound they are. If you fuse light nuclei, how strongly bound they are changes. And then that strength of how tightly bound they are, you can relate that to quote unquote missing mass and then sort of fusion energy. So that framing is the classical plasma physics framing of fusion. And this relies on thinking about smashing billiard balls into one another. And so the challenge emerges quite naturally, which is that you need to figure out a way to smash these billiard ball-like nuclei together and get them close enough to each other that that strong nuclear interaction can take over and you can get fusion. The issue is that you have this electromagnetic repulsive force in this so-called Coulomb barrier, which stunts the fusion rate. All of the different approaches to fusion are figuring out some way to cleverly smash these billiard ball nuclei together. And there's some different approaches, but basically the name of the game in fusion science is heat these nuclei up to really, really high energies, hotter than the sun. And then that kinetic energy will be enough to increase the fusion rate. Naturally, the problem with cold fusion emerges, which is in the name, cold tautologically is inconsistent with that framing of how to do fusion. So that's the first problem. And then the second problem is that fusion reactions have products. If you fuse two hydrogen nuclei, and we can take the case of deuterium-deuterium fusion, for example, so this is the classic cold fusion fuel. A hydrogen nucleus has one proton, and then depending on the different isotopes, you have normal protium hydrogen, which just has one proton, or you can have deuterium, which has a neutron also in the nucleus. And so if you think of the case of deuteron-deuteron fusion, there are expected products that come out. If you fuse two deuterium nuclei together, you have two protons, two neutrons, and this forms an excited state of helium-4, which is just an isotope of helium. And that excited state is unstable, and it will decay. And it can decay into three different branches. One branch, which is very unlikely, is that helium-4 relaxes down to its ground state by emitting a photon, a gamma ray, very high energy gamma ray. The other option is that it breaks up into a neutron and a helium-3 nucleus, or a triton, which is just another isotope of hydrogen, a higher isotope of hydrogen, and a neutron.
And a proton in that case.
And a proton. So a neutron and a helium-3, or a triton and a proton, thank you. These are the expected products. The probability of each one of those different pathways is very, very well known. It's been measured very precisely. The energies of those products are very well known. And so the other issue with cold fusion is that you don't get these expected products. Then I should say a bit about what happened in 1989, although I think that that's actually not the most generative point of discussion. It's worth saying for the history, but you don't need to rely on these original cold fusion claims. So in 1989, these two electrochemists, Fleischmann and Pons, they were doing electrolysis of heavy water. This is where instead of H2O, you have D2O, which is deuterium instead of light hydrogen, so heavy hydrogen. And you have D2O, and you do electrolysis, splitting the D2O into deuterium gas and oxygen gas. They were doing this with a palladium cathode, and palladium is a metal which is well known to absorb hydrogen and deuterium quite readily. They were doing this electrolysis experiment where you know how much current is going into the cell, you know how much electrical power is going into the cell to drive this electrolysis. And then you can put the whole thing in what's called a calorimeter, where you can basically measure the thermal power output. They ran this experiment over a long period of time. And the claim is basically that the thermal power output and the electrical power input track each other, but then at various points, the thermal power output spikes up very high. And if you integrate that over time, the excess energies that's measured is claimed to be of a sufficient amount that it's not explained by a chemical reaction and that it's nuclear in origin. And so they claimed that it was DD fusion, deuterium-deuterium fusion. The main issues that arose was One, this is theoretically impossible because you need to heat up deuterons to very high temperatures, high kinetic energies to overcome the Coulomb barrier. And two, there's a funny quote, I think, from a physicist at Caltech, I believe, who sort of said, this is BS. If this were true, the neutrons that one would expect from that amount of fusion energy, the flux would be so high that it would kill your grad student. Where's the dead grad student? I guess if you stopped there, then it would seem that this is a priori impossible. Something must be wrong. They must have measured it incorrectly, something like this. But I think that there's another way of thinking about this, which is less classical, more quantum mechanical, where instead of this billiard ball-like nuclei smashing into each other, you think about a pair of deuterons as an excited state of helium-4. And it's just a slightly different framing. In quantum mechanics, we have what we call two-level systems, excited state, ground states. You can model LEDs this way. And this sort of framing is often used for excited states of electrons, not excited states of nuclei. The importance of that framing is that in an excited state, ground state configuration, the system wants to lower its potential energy, so it wants to decay down to the ground state. And there's some rate at which it does that. The foundational paper, I believe, in Nature by Kunin and Naunberg in 1989, which calculated the theoretical maximum cold fusion rate, which was much too slow to be observable. Basically, what they're doing is they're saying, okay, what would be the rate that one would expect this decay from the excited state of a D2 molecule to a helium-4 ground state? And the answer is exceptionally long. So long that it would be like longer than the duration of the universe. Well, my background is in optoelectronics, like light matter interaction. We think about things a little bit different than nuclear engineers. So the question emerges, are there ways to accelerate that decay process? And the answer is, yeah, maybe. Oftentimes, when you talk to people in the cold fusion space or in the Lehner field, they'll start talking about something called electron screening. This was something which was not ignored in 1989. People understood that maybe this plays a role. And so some of these early papers did calculations on how electron screening enhances that fusion rate. What we mean by electron screening is that if the fusion reaction is taking place in these metal hydrides, in these metal deuterides, in the metal cathode, in that Fleischmann and Pons experiment, then you have some sort of background electron density from the metal, and electrons are negatively charged. And so you can think about that background negative charge as sort of screening the repulsion, the net repulsion from those two positively charged nuclei. So maybe they can get a little bit closer.
Is the argument here a bit like using catalysts or enzymes to make chemical reactions take place, which a priori you'd think there's no way this can happen. This is going to take 1 million years to take place. But if you add in a catalyst, then it allows different pathways to take place. The catalyst in the end isn't affected, but the reaction proceeds much more quickly. So you're saying the electron screening in some ways might be analogous to a catalyst which transforms all of biology, and thankfully is why we're all alive.
So this is what you will often hear. But if you do the calculations on this, it does improve the rates by orders of magnitude, but it's still much too slow to be observable. And so this is where we get sort of stuck, where we say, okay, we can try electron screening calculations, but it just doesn't get you anywhere close. And this is what they did in 1989. Even if you're incredibly generous and you assume really high electron screening, it just doesn't get you there. And I agree with that. It doesn't get you there. So what are some other ways we might accelerate that natural decay or fusion reaction from a D2 molecule pair to helium-4? Well, there's a paper in 1965, a Physical Review letter, before any cold fusion shenanigans, which starts to hint at an answer, which is that in a plasma environment, for example, which is the scientific domain that is wedded to the fusion energy technology landscape or fusion science field, in a plasma environment, interactions between two deuterons that are going around at really high energy and every once in a while they run into each other, those interactions are independent from interactions occurring in other parts of the plasma environment. But in a metal lattice where you have order and structure, that might not be the right assumption. And if you approach the problem a little bit differently, whereby multiple pairs of deuterons in the lattice can cooperate together, and you treat it more as a single quantum object rather than distinct, isolated pairs of deuterons, there's an interesting effect called superradiance, which is something which is not frequently worked on or studied at the nuclear scale for understandable reasons, but at the lower energy scale, at the electronic scale, It's a very common effect, been worked on for decades. And basically what this says is that if you have excited states that are able to couple to one another, then they can decay to their ground state together as opposed to separately, which can enhance the average rate much, much faster. You might expect, for example, that if you had a single excited state and it decayed at a certain rate, if you had 10 excited states, you would just expect that the decay rate of the ensemble of all 10 would just scale linearly, right? The rate would be 10 times the individual rate. But if there's a sufficient coupling between those states, if they can talk to each other, exchange energy with one another, then actually the rate can go as fast as n squared. This is what we call collective effects, cooperative enhancement. It goes by different names.
Is this something like what happens in a laser when you get collective effects that have a much bigger result than if you treat all the photons as independent?
It's very similar to a laser, but a laser is actually more complicated. It's not quite the same physics as a laser, but it's the right way of thinking about it. So when you get these collective cooperative effects, things can go much, much faster. The reason why this isn't readily studied in the nuclear physics domain is because coupling between nuclei is very difficult. They're very small, so their electromagnetic interactions with one another are quite weak. We argue that there are some coupling effects which can be facilitated by oscillations in the lattice.
That's the lattice of the palladium.
That's right.
The metal.
That's right. And we argue that if you have sufficient coupling, you can imagine scenarios, not just imagine, we've done the calculations. There's a paper in the New Journal of Physics and an archived manuscript, which I can share with you all afterwards. And this was released last year, which really for the first time did very, very quantitative calculations on this, that you can get into coupling regimes where pairs of deuterons, instead of having individual decay rates, you can treat them as an ensemble, as a group. And because oscillations in the lattice are very long wavelength, they can stretch very far out into the lattice. You can have scenarios where you have many, many, many deuteron pairs. And so while the fusion rate is quite low, if you have enough deuteron pairs in a metal hydride lattice, which can cooperate and you can get some collective effects, the fusion rate can be accelerated by tens of orders of magnitude. And so it's a very powerful tool set.
So we should come to the experiments in a minute, but just to round off this brief look at the theory, listeners who want to explore more can look up superradiance and we'll give them a pointer to the paper you mentioned. But it does sound like the quantum world defies our intuitions in many ways, and if we bring our naive schoolboy billiard ball intuitions into the play, we could be misled. And there is new physics, which is worth looking at. It could explain how these things happen. So perhaps we'll leave that theoretical discussion unless you think I've butchered it terribly in my brief summary just now.
No, I think that's right. I would just put one final touch on it, which is to say that there is a community that is increasingly interested in exploring these types of quantum effects at the nuclear scale. This is not in the Leonard field. And I don't think that these are individuals who have any sort of anticipation that their work might be relevant for low energy nuclear reactions. But I think from our perspective, we see this emerging community of, you might call it nuclear quantum dynamics or something like this, which is developing. And it really starts from this 1965 physical review letter about nuclear superradiance in the solid state. And then we see, on the other hand, that we have these decades of anomaly reports in the Leonard community, and we think that these things marry quite naturally. And that really sort of defines our work, which we think the appropriate name is nucleonics. In the same way that the semiconductor revolution found out ways to manipulate electronic states, giving us the transistor or the laser, in a similar way, we anticipate that one might be able to have such precise control of nuclear states. And so in the same way that you have electronics, you might have nucleonics, where we can manipulate nuclear states.
Well, maybe look at the experiments that you now consider to be the most interesting, the most promising. What kind of interactions are there?
Getting to the anomaly claims, one thing to say about the Leonard literature, it's vast, it's very disparate, very hard to get your head around. My intro to the field came about 3.5 years ago now. And it came from a Nature Perspective article called Revisiting the Cold Case of Cold Fusion, which was sort of a summary of a 4 or 5 year research program at Google. And I had never really taken the field seriously before reading that paper.
So Google did some serious research into this.
Yes.
And published in 2019? Basically, they seem to say that they couldn't replicate things.
Yes. So they were not able to find any proof of anomalies. But I think if you read that article, it's sort of a call to the scientific community that this is something worth exploring. Some of the people that were involved in that research are still working on it. They're not still working on it for no reason. This is something which should motivate the scientific community. We need new blood to look into these anomalies. And I think maybe one difference between what we're trying to do and what the Google program tried to do is that the Leonard literature is again, so vast. We spent a lot of time talking in the theory section about what are the problems with cold fusion, and the cold nature of cold fusion is a challenge. And then also the reaction products that one would expect from fusion reactions are unexpected. That leads to sort of a strategic question, which is, what kind of anomalies do you focus on trying to replicate in the Leonard literature? I mean, I think oftentimes people want a yay or nay answer. And I think that it's too simplistic. I started the podcast talking about embracing uncertainty. What I mean by that is giving a yay or nay on the whole Leonard literature is a huge, tall task. Instead, what we should do is we should isolate particular experiments, particular types of experiments in which there are anomaly reports, and then try to replicate those results with state-of-the-art best practices of the scientific community more broadly. And that's what we're trying to do. ARPA-E's Leonard program selected a few teams, of which we are one. In doing so, we are trying to replicate reports of nuclear particle emission or the formation of new elements in metal hydrides that are gas-loaded. So instead of the classic Fleischmann and Pons electrolysis experiment, there are also experiments where the loading of palladium and titanium samples with deuterium or hydrogen gas, people have observed and reported, for example, bursts of neutron emission, gamma emissions. If you're trying to answer the question, is there a novel nuclear phenomena, then one should focus on experiments where the claimed results are unambiguously nuclear. If these reports really are correct of neutron bursts from unloading and loading, so that means absorbing deuterium gas into a palladium sample and then deloading it, having the deuterium gas exit. If something as benign as that stimulation of loading or deloading, or irradiating the metal with a very low power laser, if something like this is capable of exciting nuclei to the point where they emit neutrons, that's a huge revolution in nuclear physics. But importantly, it's a much more tangible, observable, rather than trying to measure heat from an electrolysis cell. There's lots of calculations that you have. It's quite ambiguous. It's not obviously, heat can come from chemical reactions too. So it's not inextricably nuclear. It's like a secondary product, you might imagine. So we sort of narrowed in on a segment of the literature, and we've done pretty extensive literature review and analysis. Our theoretical work is really guided by Peter Hagelstein, who's a professor at MIT, who's been trying to explain these anomalies for a long time. He's really at the forefront of competent theoretical model, but he's also very adept in the Leonard literature, the experimental literature. And then our team has spent years, and in some cases decades, really exploring the Leonard literature, trying to find the most compelling experiments. So for example, one of the experiments in our ARPA-E program, which we are trying to replicate, is an experiment where titanium hydride particles, this is a different metal. Instead of palladium, it's a titanium metallic lattice. Titanium hydride particles are compressed into these pellets. Then these pellets are put into a vacuum chamber. The claim, and this was from a paper in 1991, I think it was in Fusion Technology, but some fusion journal, I don't remember exactly what the title was. This paper claims that when they get into certain temperature pressure regimes, you get into certain phases of the titanium lattice. So the original samples is a titanium hydride particles. You compress it into a pellet. You replace the hydrogen with deuterium. And then if you cross certain phase boundaries, so this is where the phases of the titanium lattice change. These are certain pressure temperature conditions where you get a change in the structure of the titanium deuteride lattice, that when you cross these phase boundaries, they correlated this to neutron and gamma bursts. So this is a very interesting experiment for us. The details are always very complicated, but at the surface level, there's a claim that when you have a certain stimulus that is crossing a phase boundary, this results in neutron emission. To many nuclear engineers or physicists who are listening to that, that sounds sort of preposterous. But I think for us, just to tie back to the theoretical picture, because we really try to marry the two, there's reason to believe that crossing certain phase boundaries might result in vibrational modes of the lattice being excited, which could facilitate that coupling of distant deuteron pairs. And that could result in those collective effects that I described earlier.
So how long do you think it's reasonable for the scientific community to keep an open mind on this? Because it's been going on for decades, and people keep saying, well, there's interesting ideas here, and they don't quite pan out, but there's other interesting ideas here, and they don't quite pan out. What is your forecast? What wouldn't surprise you in 5 or 10 years' time? That we'd be back here having the same conversation with a slightly different set of anomalies? Or do you think there will be a much bigger movement behind low energy nuclear reactions by that time?
Predictions are always quite dangerous. I can answer that question in different ways. One answer might be, actually, I think the scientific community hasn't really engaged with that literature much at all in the last 2 decades. Part of what the ARPA-E program is trying to do is just try to bring scientists from mainstream institutions. The institutions that are represented in this experimental ARPA-E research program are us from MIT, Lawrence Berkeley National Lab, University of Michigan, Texas Tech, Stanford. These are places where good science happens. These are good researchers. In some sense, it's sort of a call, and I think the Google program had the same sort of motivation, that actually we should get involved, that we should have more scientists engage in the literature. We don't need to make these overarching claims about when it's time to call it. These sort of yay or nay decisions come from a place of it's more comfortable if we have certainty. But the reality is that a lot of this is uncertain, and it takes a lot of work to go from each experimental type and really probe. Maybe all these experimental claims have prosaic explanations. If that's the case, it actually requires scientific investigation of these different areas. And ultimately, it comes down to this: individual scientists will make their own call as to whether or not it continues to motivate their time and effort. That's how the incentives of science work. But I would say that probably the scientific community needs a little bit more of a culture that embraces exploring the uncertain, a little bit more ambition in that regard. That would be my challenge. And I should just say, and this comes back to that last experimental report that I described, that paper, when I talk about uncertainty, what I mean is that when I read that paper, it immediately piques my interest because you have this stimulation of an inextricably nuclear effect, but then you get to the details. The reason why it's not fully convincing is because you can say that you measured a neutron. What does that actually mean? How do you actually know that it was a neutron? How do you know it wasn't electrical noise? Part of what we're doing in the RPE program is that there are best practices in the nuclear diagnostics community of what kind of detectors. Our go-to is a scintillation neutron detector, where the electrical signal that you get out of this detector, if it's actually a neutron, it will have a characteristic waveform. The electrical pulse will look a particular way if it's really indeed a neutron. This is the kind of thing where the linear literature needs upgrading, needs experimental upgrading. And so what we're trying to do is find the experiments where if there is a genuine nuclear effect, it can be really pinned down with best practices, and you can work to remove the ambiguity. The linear literature has a lot of ambiguity, and it takes a lot of experimental work to disambiguate those results. And either you find that actually you can't replicate the results, or you replicate the results, but you find that there's a prosaic explanation, or you replicate the results and you show that actually, there is indeed a novel nuclear effect going on here. And the scientific process needs to unfold for that to happen. But I would say that in general, the scientific community hasn't engaged sufficiently with that literature. They should do it more. And ultimately, science funders and scientists themselves will make a call about what they want to fund and what they want to work on. That's the world we live in.
And Jonah, how many people are there in the LENR community now?
It's in general quite an old community. A lot of people who got started working on it in the 90s. Every 1 or 2 years, there's a cold fusion conference. Some years you get better turnout, some years not so good. People doing active experiments, probably several hundred, maybe 1,000, something like this.
So that's quite big. Are these people all tenured academics?
No. I would say there's a far smaller number of what I would say like academically really rigorous and serious groups doing experiments in this space.
And the others, would you describe them as hobbyists, or how do they do it?
A lot of hobbyists, a lot of people who are retired engineers who got interested in this field, or retired professors who at one point ran a serious academic lab, in some cases working in this space. But I would also try to make the argument that when a field like LENR gets stigmatized in a certain way, Hugh Price, who is an emeritus professor at Cambridge, professor of philosophy, and worked on quantum foundations in physics, and he got interested in this space about a decade ago. I met him at my first cold fusion conference when I was still not quite sure what to make of the field. And he has this concept called the reputation trap. The field is a bit taboo. It's not maybe the best career move to go into that space. It's not well funded. There's not a lot of serious work going on. And I think that when a field is in that state, it sort of retracts. It leaves the mainstream institutions. That's always a dangerous place for a scientific field to go. Epistemic standards loosen. They're not as strong as you find in mainstream institutions and academic labs. The field has its own journal, right? It has its own conference. And in many cases, that can also be a sign of the maturity of a field. But in this case, it didn't arise from, there's so many scientific results that we need our own sub-institution. Still very much within the mainstream institutions. No, this is sort of we can't quite publish and we don't have enough grants, so let's just make our own community. And then it's become quite isolated. So you have a lot of hobbyists, not a lot of serious funding, and that's just never a good place to be in as a field. Our perspective is we need to be able to do this work, but we need to do it in serious mainstream institutions where you have funding. Some of this is practical, that you have radioisotope sources in-house to calibrate your detectors. You have good microscopes. I would say this sort of gets back to you need to be able to do this work in mainstream institutions, whether it's the reputation trap or this adopted wisdom that there's nothing to cold fusion or nothing to Leonard. I think it's something which shoots the academic community in the foot, and maybe it's a blind spot that needs to be probed a little bit more.
My final question will be if you've looked at some of the literature recently about why science hasn't been so innovative recently. There's a lot of people feeling that science is too much incremental, that when people apply for scientific grants, they have to dovetail into what's worked already. People have looked at counterexamples such as Katalin Karikó, the researcher who was for many years pioneering the idea of mRNA vaccines, so a totally different field from yours. She had this crazy idea that maybe vaccines with mRNA could one day cure cancer or could be used for infectious diseases. And she was the victim of a reputation trap as well, that this field was a dead end, was going nowhere. Thankfully, she was made of stone stuff. Thankfully, she found one or two good collaborators. And in the end, she broke through. Her research was used in some of the vaccines against COVID. And she did get a Nobel Prize. But my goodness, it was an uphill struggle. And people look at how effective is the scientific community? What are the traps in it? This is one of several examples that we are too far away from the pioneering spirit of the Bell Labs, when bright people would be given money. They wouldn't be asked to fill in lots of forms justifying exactly how sustainable and how environmentally conscious and how diverse their researchers' teams were. They were able just to go full speed ahead, come up with, the Bell Labs in particular, came up with huge numbers of patents. So have you looked at this? Do you feel a sympathy for the likes of Katalin Karikó? Or do you think you've got unique characteristics in your own LENR field?
I think that's right. I'll harp on it again, but I think this comes back to embrace of uncertainty and ambiguity. My colleague at MIT, Florian Metzler, and I, we wrote an article, it's only a preprint now, called Identifying Intellectual Dark Matter. For more transformative discoveries, we need to embrace scientific ambiguity. I have to say that intellectual dark matter is not our term, but it's a good one.
I think you should claim it anyway. It's a good one.
It's a good one. It's always funny when you have a scientific funder who claims he wants to fund breakthrough science. Usually that's anti-correlated with when they actually want to fund breakthrough science. It's always easy to sort of say that you want to fund revolutionary work or you want to support really innovative ideas. You can say that, and then when you get the proposal, it can be scary. Maybe this won't work. Maybe this is a dead end, or maybe this has been already settled, that cold fusion, for example, is nonsense. So it's always interesting how people get cold feet whenever you actually have to take that jump, because it is a jump, it is a leap, and it takes risk, and it might be wrong. And so I think we just have science funders that are not very ambitious. I think it breeds a culture in graduate students and postdocs that maybe you have a big idea, but you can't work on it until you're 55 and you have a tenure faculty position and you have a big lab and you have grants. It's not the right way. It's not an indication of a healthy scientific community where people can take those ambitious risks.
On that note, Jonah, I think we should thank you for your time and wish you well in pursuing intellectual dark matter. And thank you very much for joining us on the London Futurist podcast.
Yeah, thanks, Callum, and thanks, David. I really enjoyed it.
Look forward to seeing how your work develops and wishing that there really can be an abundance of easily accessible energy resulting from your work. Thanks.
Thank you.